what if you take this symmetry breaking operation, the polar coordinate transformation, and you add one of these symmetry preserving operations, and then you sort of extend the loop. So now our process is take an image, do the polar coordinate transformation, rotate the result, and then start over. So rather than just doing the same thing on every transformation, we now have a pair of transformations that we're going to alternate between. And so this, of course, yields a slightly different, or eventually quite different set of attractors. And so shown here on the images are the application of 10 through 60-degree rotations as the rotation step in this process. Obviously, there's something else going on here as well. There's a visualization component to how this is being done. So in this case, we start with a set of vertical lines. We apply the polar coordinate transformation. We end up with, and this is a slightly different formulation than the original, but anyway. So we end up with circles, right? So you can see actually in the background, at least for those of you who have good eyesight or are sitting close, that the first iteration is still there. There's a sort of set of circular nest of concentric circles that are present in all of these images from the first application of the polar coordinate, and of course rotation does nothing to circles, so they stay the same. And then if you look even closer, you can see where those circles map to when you apply that set of operations a second time. So there's a very light outline of another set of lines here. And then as you keep going forward, the whole thing contracts down towards, again, the attractor of this particular function. I mean, it's a two-step function, but it's still just one equation, really. And you can obviously see the familial similarity between different amounts of rotation being inserted into this process. And so, again, you can kind of work with these types of functions, this sort of operation. This color image here is a composite of 4 different functions of this sort of type, put together to please me, and with a background. And then in the lower left, you can see another way of visualizing this same sort of operation, where instead of adding a set of lines each time, we're adding a translucent gray overlay so that wherever the function moves the gray points towards becomes darker and darker on successive applications of the process. So the attractor now is the black area, and you can see the various steps in shades of gray. But again, this is fairly repetitive, right? We're just doing the same thing over and over and over again, rotating by a certain amount, applying the polar coordinate transform, or flipping the image and applying the polar coordinate transform. And there's a limited number of possibilities there to a certain degree. If you start thinking about systematically exploring all the possible space, though, you don't have to do the same transformation every time, right? You could, for example, take a different rotation each time through the algorithm. And so some of the images shown here exemplify that. So now, instead of doing the polar coordinate transformation and rotation by a certain amount, we're picking the amount of rotation differently for each of these columns with the R above them. So here we're rotating by, say, 75 degrees, and then here we're rotating by, say, 180 degrees. And so if you approach the application of these geometric transformations in that manner, suddenly there are quite a few possibilities. You'll also notice that it doesn't tend to matter in the end what shape you start with. You start with a circle, a pentagon, an X shape. They all kind of lose their original features by the time you've applied even, 6 steps. So I pretty much stopped changing what the initial image was at this stage and just went with a square from here on out. So pretty much everything that you'll see is these geometric transformations applied to something very simple like a square. So what you start with almost makes no difference at all. So if you think about a vector that describes the set of geometric transformations that we're going to apply here, you can look at it as we're going to choose a symmetry breaking operation, such as polar, inverse polar, or circle inversion. And then we're going to choose a rotation, and we'll alternate between those 2 steps. choosing our rotation in some manner. And you can end up with, you can notate that as sort of P1R1, P2R2, and so on. That you can think of that as a vector, or later on we'll think of it as a genome for that particular image, right? It fully describes, with the rest of the algorithm in place, how to create the particular image that we're getting to. And so on the bottom two images, we have the results of polar 135-degree rotation followed by polar 30-degree rotation repeated 4 times. If you could show movie number 1, please. So if you have a vector that goes through, then obviously that describes a space with n dimensions. And so you can think about traversing that space by changing one of the dimensions, the rotation in one of the dimensions, and calculating an image at each small increment of rotation. And so doing that, you can see that there's actually quite a wide variety of different shapes, that, or at least it seemed to me, quite a wide variety of different shapes that are generated from fairly small changes in how the image is constructed, right? And so that, of course, when you start going back to thinking about a systematic exploration, leads to a combinatorial explosion, right? If you try and enumerate every single possible squiggle that you could get out of this system, you're rapidly going to fill your hard drive. And I generated, a few tens of thousands of these things, and then it's like, okay, wait, this is ridiculous. I can't look at them all. But what I did discover was that there is, as I say, at least to my eye, lots of variety, and you cannot say that just by looking at a few hundred of these things, you've seen all of them. So what do we do about that? Well, what we're faced with is a very large parameter space, right? If you think about this vector that we talked about constructing, or the genome of this particular image, we've got now a very large high-dimensional parameter space. In fact, at that point when I was working with this thing, I figured that there were probably 10 to the 25th possible images that one might construct here. And so obviously we need to look at a subset. How do we find the interesting images? How do we find the ones that are different from each other? There's a lot of possibilities. You could think about clustering the vectors or doing something like that. There's lots of work in chemistry, actually, on how you cover a very high dimensional space to sample it well. But the take-home message from all that work typically is you can't. So the approach that I took was to try a genetic algorithm. So we start with 1,000 random sequences, make visualizations of each of the images that result from those sequences, review and score each one based on my personal feeling about whether it was interesting or novel or attractive, and then take pairs of those images and recombine them weighted for the score that was attributed to them, and generate a new generation and recycle. So here's a pipeline pilot protocol that I wrote to generate an initial set of 1,000 or so diverse starting points for doing this kind of exploration. So in this particular protocol, we generate 10 times as many random sequences with the first 2 components as the ultimate number of images that we want to generate in the first generation. And then we filter out any duplicates using one of the components that's built into the system. And then we use a clustering algorithm to, as I was talking about earlier, find the centroids of the vector space where these randomly dropped points are in this high-dimensional space, so that we try to cover as much of that space as possible with this first 1,000 images, so that we're accessing, as much of the space, as many different kinds of images as possible. So we cluster them with average cluster size of 7, and we output only the centroids of the clusters, and this becomes our initial sort of set of images that we're going to work from. Now, having done that, of course, we got to figure out how we want to render these things. There's lots of different ways that I've experimented with. I've talked about a few of these. Obviously, you can just do black and white. You can do colored versions of the rendering. starting with a colored square, which I'll show more about in a second. You can do this sort of grayscale layers approach. You can switch to blue scale, right? That makes it kind of more interesting in some ways. You could do a color swatch and then layer that over top each time, and you can end up with some interesting results that way, as shown in the lower left. What's interesting about starting with a colored square where the different locations in the initial image have different colors is that you can track back from the final image to where that pixel actually started out its life, right? So you know that anything that's orange started out in the top right-hand corner of this image. So when you get down to the bottom and you can see the sort of, I don't know, the abdomen of the guy down there in the lower right is orange, you know that that's where that particular part came from. So you can show movie number 2, please. So this is another traversal of the parameter space for a particular group of these images generated by these vectors. And the movie pauses at the particular sort of keyframes that were images that I had found in exploring some of this parameter space, and then animated between. And in this case, we're not traversing sort of Manhattan style, that is one dimension at a time, but rather going as the crow flies through the vector space, so changing lots of different rotation vectors all at once. So just more different ways of visualizing these kinds of things, and especially as you get into relatively long sequences of transformations. So the one on the left, I think, is the result of 28 transformations sequenced together, and each time adding a sort of a veneer of sort of a rainbow of pink and yellow on top of what was already there. And on the right-hand side is a similar approach. This one on the right-hand side takes more advantage of what I call chop, squash, duplicate, which sort of takes an image, cuts a piece of it away, squishes it down into half of the image, and then duplicates it. So that actually is a symmetry generating operation, where before we were talking about symmetry preserving or symmetry breaking. If you think about reflecting something over top of what was already there, in a sense, that's a symmetry generation process. Okay, so then having generated 1,000 or so images in a generation, I need a way to review them, and it has to be ergonomic, right? I mean, I don't want to have to open each image manually and then type in a value in an Excel sheet and figure out which row it belongs on and all this sort of stuff. So I wrote another pipeline pilot protocol to automate this process. And so what this protocol does is it goes to the most recent generations folder. It sort of looks in the master folder and finds the largest numbered generation that exists, lists out all the images that are there with the list files component filtered on .png, makes one page worth so that I can fit it into a browser page, which I found that 50 images at a time was a good amount to work on. And then we go into the sub-protocol that's boxed there. So at this stage of the pipeline, we move down here. And here we actually use some of the imaging component collection, which was one of the things that I worked on when I first joined the company. So I was pleased to use that to read in the image and put it into a web page accessible format. We join from our database of sequences what the actual sequence that generated this image was, so that if you want to look at it if I wanted to look at it while I was rating the images, I could see what the actual sequence was, although I did debate with myself about whether it was a good idea to show that or to hide it so that I would be unbiased by what the equation was. I opted for showing it in the end. And then we add some form elements that allow easy addition by the user, me, of what the rating is. So in this case, all you have to do is hit a number key and then hit tab, and it jumps you down to the next list element on the page, and it's formatted in such a way that jumps you down one entire page and shows you exactly just the one next image that you have to rate. So it becomes fairly fast and ergonomic, so you just hit the key and hit tab, and you can go through these things quite rapidly, which is important if you're trying to do thousands and thousands of them. And this is what the user interface looks like. And this is rescaled to make the point here. But so here's 3 images from a relatively recent run. And then the user interface elements shows you the number of the image, the transformations that were applied to get there, and then your list box of available ratings, and then where that image is on disk. I've never really needed that, but it's there. And when you get all done rating all the images in the generation, then the system goes back and it gives you some statistical analysis of what the ratings for this particular generation were. How did different lengths of sequence affect what you thought of the images? How many 1s, 2s, 3s, 4s, et cetera, did you give? And which were the actual geometric transformations that were associated with the highest rated images, that sort of thing. So that's kind of interesting. Again, getting back to how you want to visualize these things, you can, because the transformation proceeds in steps, it's not just one equation, but the nested functions are actually executed sequentially. You can display the antecedent images for any final image. So shown on the left-hand side, this black and white image is immediately preceded, the large one is immediately preceded by the one on the lower right, in the smaller image. And you can see, well, you can guess that this is an inverse polar coordinate transformation that results in sort of unwinding this circular shape into a flattened out or unrolled shape. Whereas that lower right circular image comes from a polar coordinate transformation of the preceding image and so on. And then on the right-hand side, you can see all, whatever it is, 42 steps that take you from a black square with a rainbow background all the way through to whatever this looks like to you. And I don't know, to me it looks like a strange tree on a cloudy day or something. But so that's how you get from the very beginning all the way through to the very final image. So we've now generated some initial images. We've actually done the visualization and we've given them a rating. Now we need to create the next generation of images. And so here's a protocol that does that. So we read all the ratings data, and then we apply a weighting. In this case, I was actually just taking the cube of the rating that was given for every image, and then we make sort of a pool of parent images, right? Parent sequences. You can think of them as genomes, right? So these are the genomes of all the parents that are available for every new image that you want to generate. And then we, in pipeline number 2 here, we generate however many records we want to create new images, and we pick 2 parents just by, now here's where we do some random operations here, but just to pick the parents from the pool, right? So they're weighted and we just pick one image from, or one pair of images from the pool. We get the sequences for those 2 images in the 2 join operations, and then we put them together to make a new sequence. And I'll show a bit about how that's done in a second. The next thing we do is we make sure that we aren't duplicating an image. So again, the first occurrence filter to make sure that the code that I'm going to make is not duplicated in this set. And then also there's another join data from master cache component here. So this is just a join component that looks in the database of all the images based on their codes that have been generated before, and make sure that I'm not repeating anything that had been done in an earlier generation. So anything that passes, right, anything that has a match gets filtered out. Anything that fails, that's a new thing, so we can go ahead and create that. So then we add them to the database and visualize statistical properties of the new set. Here's a little bit of the code that actually does some of the key steps in calculating the new sequence of transforms from the old sequence of transforms. This calculates the length of what our new sequence is going to be, because of course the genomes aren't necessarily the same size, right? So the vectors aren't necessarily the same size for any 2 images. So we calculate a split point. We take the first part of parent number 1 and we take the second part of parent number 2. We stick them together, and that's our child sequence. Very simple. in order to make sure that we didn't get caught in local minima or in a rut, right, that we didn't have inbreeding, we added some, or I added some mutation and drift to these sequences. So this is instantiated in 3 different ways. So we have drift for continuous operations, right? So something like rotation, you could imagine drifting from polar and then a 30-degree rotation to a polar and then a 40-degree rotation. So this is going to give you a similar image, but not exactly the same, right? And certainly the earlier it is in the process, the less recognizable as a close relative it may end up being. You can have mutation, particularly useful for transformations that are discrete, right? So polar, inverse polar, circle inversion, these sorts of things. You can't really drift from one to the other, you just have to jump. So for example, shown below, you could have polar and then a horizontal flip, or you could have an inverse polar and then a horizontal flip. And these can make quite a large difference. And so we employ these, or I employ these with diminishing frequency as the changes get more radical. And then of course you can just extend the sequence by tacking on a random one at the end of the genome of the child.